Today we'll be talking about a few topics simultaneously in probability theory. And it's going to be great because I love these. I love probability. I love Gaussians. I love the Central Limit Theorem. You're going to love them too. It's going to be great. Actually, in some ways, the reason for this lecture, besides covering these great topics, is preparation for the next lecture when we're going to talk about Chernov's bounds, which is like one of the most ubiquitous tools in theoretical computer science. But I think you can't really properly appreciate the context for them unless you see some stuff about Gaussians and the Central Limit Theorem first. So a very typical scenario in theoretical computer science is you have something like an algorithm that is probabilistic, and it quote unquote succeeds with some probability p, and then you run it a bunch of times independently, and you want to understand something about the total number of times it succeeds. So that's the context for all these topics that we'll talk about today. So let me write this down as setup. Okay, so let x1, x2 through xn be IID. I'll remind you what this is in a second. Random variables. Okay, so IID is some abbreviation that's very popular in math, less so in computer science, but it stands for independent and identically distributed. So the main thing is that they're independent random variables, and identically distributed means they all have the same distribution. It's a very common scenario. And in this setup, they're just going to take values that are either 0 or 1, where 1 is considered a success. Okay, so they're going to have these properties. The probability that xi is 1 is p. And as I mentioned, they're only going to take the values 0 and 1. So therefore, the probability that xi equals 0 is 1 minus p, which is, we'll call q, like last time, actually. Or mathematically, this is to say that each xi is a Bernoulli random variable with success probability p. And we're going to let s denote their sum. Let me actually write s sub n to sort of remind ourselves that it's the sum of n copies of this random variable. So Sn is also a random variable, and its meaning is it's the number of i's such that xi is 1. Okay, and our goal is to try to understand this s, random variable, properties about it. So let's start with the basics. Whenever you have any random variable at all, like the very first thing you should strive to do is understand its expectation or its mean. These are synonyms, expectation and mean. Okay, so can somebody tell me the expectation of s of n? Who said it? Pn, yeah. What's your name? Sunny. Yeah, hey, Sunny. Yeah, Pn. That's right. Again, the way to see that, a good way to see that is by the rule linearity of expectation. Okay, which says that the expectation of a sum is equal to the sum of the expectations. And for this, we don't even need independence. I stipulated that they're independent random variables, but this is true even, linearity of expectation is true even when the random variables are not independent. Again, each of these random variables has expectation p because it's 1 with probability p and 0 otherwise. That's great. So now that we've got that, the second thing you should always strive to do whenever you have a random variable is to compute its variance. That's the next step up. Somebody know the variance of this random variable? Yeah? NPQ, right. What was your name again? Keith, right, thanks. NPQ, that's true. I'll say why. I mean, maybe this is one that you don't necessarily immediately have in your head. In fact, let me review variance a little bit over here. So, what is the variance of a random variable? I'm going to call the random variable y here so it looks generic. The variance of random variable y is this expected squared deviation from the mean. So it's this quantity where I'm writing mu for the mean or expectation of y. Okay, so that's somehow the meaning, how much it deviates from its mean, squared wise. There's also a sort of a formula for it. It's the expected value of y squared minus the expected value of y squared, where those two things have different parenthesization. Good, so it's a measure of how much the random variable fluctuates, and let's recall some basic facts about it. One important basic fact, which is the main fact you need to do this calculation, is that variance is also additive. But for this, you need the assumption that the random variables are independent. Okay, so in our situation, S, extends to the sum of more than two random variables, which is the sum of independent random variables. It means the variance of S overall is the sum of the variances of the individual xi's. So actually, we can calculate that easily. Let's do that here. The variance of an individual xi, well, let's say using this formula because it's easier. Each xi has a property that xi squared is the same as xi because it's just 1 or 0. So the expected value of xi squared, it's 1 with probability p. And then we know its expectation is p, so this is p minus p squared, which is p times 1 minus p, or pq. Okay, so that's how we can derive this. Let me also just record a couple more facts about variance that we'll want to remember. If you take a random variable and add a constant to it, that does not change the variance. Variance is translation invariant. I guess that sort of follows from this one technically, because a constant is a random variable that's independent of everything else and it has 0 variance. But it's good to just remember this one on its own. That's if you add a constant to a random variable. What if you multiply a random variable by a constant? What happens to the variance? Yeah.
C squared variance.
Right. What was your name?
Ian.
Ian. Thanks, Ian. Yeah, it's a funny one. It goes up by c squared, as you can see from like this formula, for example, or the other formula. Good. That's most of the properties of variance that I want to remember. Actually, let's remember one more thing, which is the standard deviation of a random variable is just the square root of the variance. Okay, and this is often denoted sigma. If this one is denoted mu, which means we denote variance by sigma squared. So sigma S stands for standard deviation, mu m stands for mean. And standard deviation we like because, if y has units like it's y dollars, then the units of variance would be like dollars squared, which is weird. So you take the square root to get back to regular sort of units. And you might ask, why don't we just put the absolute value here or something in the first place? But absolute value is like a disgusting thing to work with. This is a nice, when you square something, it's a nice polynomial, so it makes calculations nice. So this is why things are defined the way they are. Okay, great. Any questions? Okay, so here's another sort of life pro tip, if I may offer one. As I said, once you have a random variable, you should figure out what its mean is. You should try to figure out what its variance is as you can. And then if you can do both of these things, you should standardize your random variable if you can. And that means make it have mean 0 and variance 1. Like the best, most enjoyable mean for a random variable to have is 0. And the best and most enjoyable mean for a random variable to have, variance for it to have is 1. And you can kind of arrange for that by doing some trivial operations to the random variable, and these operations are called standardizing it, which I will explain to you just now. So if you have a random variable, like in our case, s sub n, I'll just do it for this particular s sub n. The first thing is to get it to have mean 0. You subtract the mean from it. Okay, so this is in general the mean of the random variable. This operation is sometimes called centering. Okay, that's a trivial transformation of the random variable, but it makes the new random variable have mean 0, which is pleasant. And then you should take this and get it to have variance 1. So actually, subtracting this mean doesn't change the variance, right, by this bullet point. And then you can mess around with the variance by multiplying the random variable by a constant, which is also a trivial transformation. So what constant should we multiply by to get the variance 1? Yes?
1 over standard deviation.
Yes, very good. What was your name?
Jin.
Yeah, you should multiply by 1 over the standard deviation or divide by the standard deviation. Okay, so in our example here, that was that would be root NPQ. Okay, in general, this is the standard deviation. Okay, and that makes a random variable which has mean 0. This also doesn't change the mean, of course, and variance 1, and therefore also standard deviation 1, which is really convenient. Okay, so in general, if you have any random variable, you might define S, you might define Z as the standardized version to be S minus mu over sigma, where these are the mean and standard deviation of S. Okay, and that's great because it's a convenient mean and variance to have, and it doesn't lose any information at all about the original random variable. So if you really care to understand everything there is to know about S, it's necessary and sufficient to understand everything there is to know about Z. Just because, I mean, you can understand everything there is to know about S by understanding the probability that S is at most U for every value U. That sort of completely defines the random variable S. But S is just a simple linear transformation of Z. This is the same as the probability that, I guess S is mu plus sigma Z plus the U. And then we can invert this. We get this is the probability that Z is at most U minus mu over sigma. Okay, and mu and sigma are constants here. So if you ever understand everything about the distribution of S, then you also understand the distribution about Z and vice versa. Okay. So let's go back to this example of our particular random variable Sn, which is the sum of n independent Bernoulli random variables. That's 0, 1 random variables with probability p of being 1. And let's even focus in on the most enjoyable special case when p is a half. Okay, so this is like the case when you're flipping a fair coin n times. Let's consider the case p is a half, which also means q is a half. And in this case, this random variable Sn, it's like a random variable representing the number of heads, let's say, when you do n fair independent coin flips. So its mean, as we see from up here, is n over 2. And its standard deviation, well, its variance is n over 4. And therefore, its standard deviation is root n over 2. Okay, you should really, for like non-ridiculous random variables, you should think of the standard deviation as like the amount by which the random variable sort of typically or standardly deviates from its mean. And this is true. If you flip n coins, you expect the number of heads to be like n over 2, but it should fluctuate within a range. It's like a few constant multiples of root n, typically. Which is consistent with this fact we learned last time, that if you flip n coins, the probability that you get exactly n over 2 heads bang on when n is even is proportional to 1 over root n. Because if it's going to be like fluctuating in a range around n over 2, a few multiples of square root n, maybe they should all be equally likely. In fact, probably them landing right in the middle is the most likely case. So that should occupy like a 1 over root n or so fraction of the probability. Okay, so now this sort of life pro tip told us that this Sn is fine, but we should really maybe standardize and look at, I'll call it Z sub n, which is S sub n minus n over 2 over root n over 2. OK, let me multiply top and bottom here by 2 and factor out 1 over root n. No, actually, let me not do that. Yeah, let me multiply top and bottom by 2 and factor out 1 over root n. So I get 2 Sn minus n. Did I do that right? Yeah. And this is, let me write it like this. 2x1 minus 1 plus 2x2 minus 1. Oops. Plus dot 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 plus 2xn minus 1. Okay, that's sort of a funny way of writing this expression. And the reason I do that is, you see, now look at these random variables here. These are nice random variables too. These random variables, 2xi minus 1, half the time it's 1, half the time it's minus 1. Okay, so these are all like random variables which are like plus or minus 1 with equal probability. Such random variables are called Rademacher random variables by fancy people. And this turns out to be like the more pleasant thing to study than the sum of n random variables that are 0 or 1. It's to study the sum of n random variables that are equally likely to be plus or minus 1, and also divided by root n. That's a convenient normalization to put in too, because this big sum will have mean 0. That makes sense if you're adding up random plus or minus 1 random variables, and also variance 1. And as I said, if you want to know anything about Sn, it suffices to know the analogous thing about Zn. So for example, last time we were looking at the probability that Sn is exactly n over 2. Okay, this is assuming, as always, that n is even. The probability that you get exactly 50-50 heads and tails. And which event about Zn is this equivalent to? Yeah?
It should be 0.
Yeah. What was your name?
Chris.
Thanks, Chris. It's equivalent to the probability that Zn is 0. And as I mentioned last time, this is asymptotic, as it turns out, to root 2 over pi times 1 over root n by Stirling's formula. Or, less precisely, it's big theta of 1 over root n. OK, so one good thing about this Zn random variable is you can make like n larger and larger and larger. And when you do that with Sn, you get random variables that take larger and larger and larger values. But Zn is like nicely set up so that it always has variance 1 no matter what n is. So nice things happen when you take n to get larger and larger and larger. And one thing you can do is plot, the histogram of Zn's probabilities as n gets bigger and bigger and bigger. And when you do that, you'll find they look like, this. Okay, let me. They follow this trend that kind of looks like this. Okay, and it's exciting to do this with an actual computer and look at it, and you'll see as n gets really big, it looks like this most famous bell curve, right? And this number up here seems to be something like 0.4-ish. And it really goes down to 0 very quickly. Actually, the maximum possible value of Zn is root n and minus root n. And Zn is taking on values that are integers divided by root n. In fact, there's a parity thing. So like the width of these bars is going to be like plus or minus. Well, I guess the width of the bars is going to be like 2 over root n. That's the width of one of these bars. Okay, and well, when you see this plot, you're like, clearly this is converging to like the Gaussian random variable. Okay, It's converging to a real valued random variable. You know, Zn takes on like a finitely many discrete values, but like it's obviously getting approximated by a random variable that's taking on real values on the real line. And the fact that this is true is the subject of the famous Central Limit Theorem, which I will now state. Actually, I can leave this up. Okay, so this is the Central Limit Theorem, or CLT. Now, the word center has a lot of technical meanings in math. Does anybody know why it's called the Central Limit Theorem? It's because Polya, who named it, just thought it was like the most important limit theorem. So it's the Central Limit Theorem. So it's like just the regular old English meaning of central there. Okay, so Central Limit Theorem concerns you have a sequence, x1, x2, actually an unending sequence of the IID, independent and identically distributed random variables. Okay, so for example, these Bernoulli coin flip random variables, or any random variables that technically have a mean and a non-zero variance. Then the associated random variable Zn, by which I mean the one you get by adding up the first n of them and then standardizing, so that Zn will have mean 0 and variance 1. Its distribution approaches, in the limit as n goes to infinity, that of Z, which is a standard Gaussian random variable. And I'll remind you what that is later, but it's like the most enjoyable continuous random variable, the random variable whose PDF is that bell curve. And what is the sense in which these discrete random variables approach this continuous random variable? In the sense that for all real numbers u, the probability that Zn is at most u is equal to, running out of space here, the probability that a Gaussian is at most u plus or minus little o of 1. And this little o of 1, let me say it properly, is with respect to n going to infinity. Okay. So that's the famous and grand and central limit theorem. And one thing I'd like to remark about this theorem is it's basically useless. So this is a remark. Okay, not completely useless, but I find it kind of hard to conceive of a scenario in theoretical computer science where you could actually use this theorem. And the reason is it doesn't give you any information at all about the rate of the error. It just says that it's tending to 0 as n goes to infinity. And the statement does not say anything about it. It's not like 1 over root n or 1 over log n or 1 over log star n. You don't know anything from the statement of the theorem. And in fact, furthermore, the way it's stated, this rate could actually depend on u, which is that would kind of stink. So it gives you very little information. There's not a lot you can do with it. But by the end of the lecture, I want to fix that by telling you the good version of this theorem, the version that has actual error bounds. And that version is called the Berry-SAN theorem. So we'll get there eventually. But we'll do a few things. We'll talk about Gaussians for a while first. Actually, another deficiency of this theorem is that it only is true as stated for identically distributed random variables. And that's a bit restrictive. Like, you don't always have identically distributed random variables.